Sometimes I like to play, how could the professor possibly catch me unaware? How could the professor stump me on a problem like this? There are a couple of ways. Some of them are mean. It's not, in fact, possible, in general, if we write just whatever numbers we want to. We can't always expect that this kind of factoring is even possible to begin with. For example, in the very first problem up here on the top, what if instead of a plus 18 in that spot, what if I had minus 18? Even a small change like that. So now you would rack your brain and say, well, how do I split negative 18 into a pair of factors? And so we could list all the possibilities. Negative 18 and 1, negative 9 and 2, negative 6 and 3. And then continuing from there, negative 3 and 6, negative 2 and 9, and negative 1 and 18. So here are all the different possibilities. And then I need a possibility where those factors add together to give me negative 9. Well, if I add these two, I get negative 17, negative 7, negative 3, positive 3, positive 7, positive 17. There are no pairs of factors of negative 18 whose factors add together to give me negative 9. So in those cases, this is just simply not possible. That's the bad news. Factoring is great, but it doesn't always work. In fact, in a very real mathematical sense, it almost never works. But in most algebra classes, we set it up in such a way that the problems we're going to ask you, by and large, are factorable. Especially if that factorization is a tool to do something else, we'll make sure that it's always set up in a way that it will work. So that's one possible curveball that I throw, but at least the solution to that is fairly straightforward, right? We just can't do it. So let's do one more curveball before we move off of this topic. What happens if the middle term isn't there? So here's an example. What if I want to factor z squared minus 36? Well, let me get your thoughts on this. What are we going to do if the middle term is just missing?
Just in parentheses, would you just do z, just what we did before, the two parentheses?
Okay. So yeah, let's try approaching it in the same way, right? Let's imagine that we're going to factor this into a product of two binomials. The z squared is still going to split into a z and a z. But now the degree of difficulty, the burden of proof, is that when I carry out this multiplication, I need for there to be no term here in the middle. So if I were to FOIL out what's over here, then the result of my FOIL needs to result in something that only has two terms instead of three. So it's not a trinomial, in fact, in these cases. But we could still play the same game, and I can ask you, tell me a pair of numbers which multiply together to give me negative 36. How about negative 6 and positive 6? That certainly works, right? It multiplies together to give me negative 36. And then in my grid, I'm going to have negative 6z up here, positive 6z down here. And what's going to happen if I multiply this all out? I'm going to get a z squared in the upper left. I'm going to get a minus 36 in the lower right. And then my other terms, what's going to happen to them? They're going to cancel out, exactly, which is what we want, right? Because in the end of the day, we don't want there to be a visible middle term in the middle. So our approach still works. We just have to have the faith and the confidence to actually follow it through. Right? It works because, and it worked because 36 here was what kind of number? It was negative, first of all, which is why we got away with having a positive and a negative term that can cancel one another out. But not only that, that positive and negative term had to be the same value. Right? They both had to have a 6 in here in order for them to cancel. But that means that when I multiply them together, I get a number, 36, which is what we call a perfect square. So this worked because 36 was a perfect square of the number 6. Right? If I change this to be 35 instead of 36, then we would have been kind of stuck. Right? Because even if we had plus 5 and negative 7, or something like that, that multiplied to negative 35, that plus 5 and that minus 7 aren't going to cancel one another out when I'm add them back together. So this method is going to work for us provided that that number at the end is a perfect square. So for that reason, sometimes this method is called the method of the difference of two perfect squares. The perfect squares part, I hope, is kind of evident, but the difference part explains why this needs to be a negative, it needs to be a subtraction sign. Difference of two perfect squares. And it needs to be that subtraction sign because in order for that middle term to cancel out, we need our two terms in the diagonal here, we need these to have opposite signs. One needs to be positive, the other needs to be negative. And that's only going to happen if their product is a negative number. If I change this to z squared plus 36, now I am re-stuck. Because now my two terms have to have the same sign. And in either case, if I add together those two terms with the same sign, they're not going to cancel like we want them to. So in fact, z squared plus 36, we can't factor in any way, at least in this course. So when it says difference of perfect squares, both of those things are necessary. It needs to be a difference, it needs to be subtraction, and both of the terms in that subtraction have to be perfect squares. 36 on the one hand because it's 6 times 6, but then also z squared because it's z times z.
So what was the answer if it was like -35?
Oh, if it was negative 35, then we can't factor it. Yeah, we're stuck. That one doesn't factor in the ways that we're factoring in this course.
I would disagree.